Hi Year 12 Maths General students. This lesson is from Unit 4 of the Queensland Senior General Maths syllabus, and today we're looking at using recurrence relations to model an investment annuity. The lesson objectives today is we're going to learn how to develop a recursion relation to model a balance of an investment annuity after a certain number of compound periods. We're then going to look at calculating the total amount of interest that's been earned since the initial investment. And finally, practice solving some problems that involve investment annuities using recursion relations and interest calculations. And last lesson, we looked at loan annuities that involved paying off reducing balance loans. For this lesson, we're going to focus on investment type annuities, where we're depositing regular payments into a savings or investment account, or we may be receiving insurance or superannuation payments. Again, the payments can be made weekly, monthly, fortnightly, quarterly, yearly, or at any other regular interval of time. When we looked at loan annuities, there was only one type of scenario where you're slowly paying a loan off over time. With investment annuities, the idea behind investment is to grow a sum of money over time, where someone might be depositing an amount of money into an account, which would be a compound interest account. And during that time, the investor might also choose to deposit regular payments, which will add to the principal amount. The main difference between loan annuities and investment annuities is that loan annuities, you're essentially making regular payments to pay off an amount of money you've borrowed. And then once you get to that zero balance, you're done. Investment annuities are different because they usually have two phases. A deposit phase. Firstly, an investor would look at depositing a certain amount of money into a compound interest investment account, which will earn interest over time. On top of that, making regular payments or deposits into that account, which will add to the amount of principal earning interest over time. There's nearly always a second phase in investment annuities, where the investor may have set a target and has reached that target of money, and now they go into what we call a withdrawal phase of the investment. So the money's still sitting there in the account earning interest, but instead of adding regular payments, the investor will withdraw regular payments instead. And this very closely mirrors what happens in a reducing loan balance. All right, so how do we develop recursion models to represent this deposit phase and withdrawal phase? Similar to what we saw in our reducing balance loan recursions, we utilize a combination of arithmetic and geometric sequences that we saw earlier. And in the deposit phase, you'll find on your formula sheet this recurrence relation for annuities. This, though, is just for the deposit phase. And you'll see the familiar AN plus 1, so our next consecutive balance, is equal to R, which is our interest that's being applied, multiplied by the current balance. And instead of minusing, we add on this regular repayment, represented by plus D. If we want to use recursion to model an investment annuity during the withdrawal phase, we simply just use the recurrence relation for reducing balance loans, because this is what we are doing with our investment. The investment is still earning interest on the current balance, so we still apply our R interest amount, so the 1 plus interest rate over 100 by K. However, instead of adding to the balance of the loan, in withdrawal phase, we are minusing regular payments. So these two formula are what we will use when we're considering our deposit phase and withdrawal phase of the investment annuity. All right, let's look at some examples to put this into practice. The first example we're looking at here involves superannuation. Now, most of you probably don't know much about superannuation. Put in really simple terms, superannuation is an amount of money that employers are required to pay on top of your normal wage or salary into what we call a superannuation account. So in this example, we've got Jessica starting a new job and her employer is required to pay 9.5% of her gross wage into her superannuation account every month. If Jessica's gross wage is $8,000 a month, what's the value of the superannuation annuity deposit by the employers? And then secondly, if interest within the super account is earned at a rate of 3.8% per annum, compounding monthly, we need to construct a recurrence relation for this annuity and calculate the balance of Jessica's super after working for 7 months. Alright, so let's look at what information is important to help us solve the problem. So the employers are required to pay 9.5% of the gross wage. So this is going to be used to find out the superannuation amount, given that her wage is $8,000 a month. Alright, so when I write that down, we're simply just whacking that into our calculator because we know that that's 0.095. Of means multiply in maths, and 8,000. That means the employers are making regular payments of $760 into her account. Setting up the recursion relation, I know that my A0 is going to be $0 because she's starting with a balance of 0. The interest we've seen up here, which gives us a rate of 1.00317-ish. And I know that my regular deposits are 760. So my recurrence relation is going to be AN plus 1 equals 1.00317 times my previous balance and add on $760. So we know our starting balance is 0. To work out the balance after the first month, we're going to take an interest of that $0, which we know is 0, and add on $760. So after the first month, she'll have a balance of $760. Now remember when we did reducing loan balance recursions, we could set up the iterations to work for every recursion in our calculator. So what we did was we took our initial balance, so in this case is 0, entered it in to the storage of the calculator by pressing 0, and then we want it to use the previous answer, so we'll just go times, enter in our rate, and add on that recurring payment of $760. So you can see that gave us our first month, second month, third, fourth, fifth, sixth, 7th month. And that will be the balance in the account after 7 months. Okay, and this is all you would need to show for working, because as long as we can see that you're demonstrating the calculation, showing us that you're repeating that calculation is just fine. So by the end of the 7 months, Jessica will have $5,370.86 in her superannuation account. For our next example, we've got Chris who's invested $8,000 into an investment account at 3.5% per annum, compounding yearly, and he also makes additional deposit payments of $500 every year. Determine how much he'll have accrued into the account over 5 years using recursion. So the $8,000 is his principal, 3.5% is our interest rate, compounding yearly, K value is 1, and his additional payments will be our D value. To find out how much he's accrued into the account after 5 years, that means we're after our 5th recursion. Okay, so great idea to write down your facts. And then the first thing we need to find out is what is our recursion relation. So AN plus 1 to get our next consecutive balance, put in our rate times the initial balance and add on that deposit of $500. So starting off, our initial balance is $8,000 After our first, we're simply applying that rate to our balance of 8,000 and adding on the 500. Again, popping that into our calculator. Remember to store our principal amount, then use the answer with the rate and the deposit added on. So there's after the first year, second, third, fourth, fifth year, the balance will be $12,182.72. Our friend Chris will have $12,182.72 in his investment account at the end of that 5 years. So far, we've only considered examples of that deposit phase. This next one's looking at involving firstly a deposit phase and then afterwards a withdrawal phase. So let's read through it. An investment of $6,500 is made at an interest rate of 7.2% per annum, compounding half yearly, with regular deposits of $400 every 6 months. Firstly, we've got to use recursion to determine the number of years it will take for the value of the investment to exceed $15,000. Secondly, determine the balance of the investment after 4 years. Both A and B will be considering the deposit phase. And then lastly, after the 4th year, deposits were stopped and then withdrawals of $650 occurred every month. Determine the balance 6 years after the investment began, and this clearly considers the withdrawal phase of an investment. Okay, so after writing down all my facts, I need to know the R or rate. So if I put that in my calculator, it's 1.036, which enables me for A to develop my recursion relation for the deposit phase. So writing that out, AN plus 1, so my next consecutive balance will be 1.036 times my previous or current balance plus $400 for every recursion. So setting that up on my calculator, I would pop in my initial amount or principal, and then I'm going to carry that forward for my recursion process. So 1.036, add on the $400. That gives me, after the first 6 months, I would have $7,134. The next time I apply that, this would be after a year, because every recursion is 6 monthly. So I'd have $7,790.82. And then the question wants to know how many years it will take for the investment to get past $15,000. So after 1 year, I'm not even up to 8,000 yet. So let's keep counting the number of recursions it takes. And if I consider that every recursion is 6 months, I should be able to figure out how many years that's converted to. Through 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th. So between my 11th and 12th recursion, the balance has exceeded the $15,000. Okay, so by the 6th year, the investment will exceed the $15,000. Okay, so let's look at B. It says determine the balance of the investment after 4 years. So again, we'll just use that deposit phase recursion. So when you think about it, if it's compounding every 6 months, if I'm interested in the balance after 4 years, I'm after the 8th recursion. Because you've demonstrated this recursion process before, all you'd need to do is just write down the 8th recursion. So remember, if we started off with the 6,500, enter that in, times it by your rate, and the fact that you're depositing 400 every time. So there's 1, 2, 3, 4, 5, 6, 7, 8th recursion. So after 4 years, there would be a balance of $12,259.22. Lastly, after this 4th year that we've just worked out, deposits are stopped and now withdrawals of $650 will occur each month. Determine the balance 6 years after the investment began. So this is where we now have to change our recursion relation to look like that reducing loan balance one. Okay, so the only difference is that instead of adding on a regular deposit of $400, we're simply minusing the regular withdrawal of $650. Because you have to remember the balance that's still in the account is still earning interest at that 7.2% per annum. Okay, so what happens now is that our new principal amount becomes the balance that we finished off with after 4 years. So that's $12,259.22. That being the new principal, I simply just apply the recursion formula to that. And I'm interested in 6 years after the investment started. So that means that I'm finding the balance of the investment 2 years after I've implemented a withdrawal phase. So this means for this particular recursion, I'm after the 4th recursion, since compounding happens every 6 months. Because you're applying a new recursion formula, make sure you demonstrate a calculation. So enter in your new principal amount, multiply it by the existing rate of 1.036 and minus the payments that are coming out now. So after a further 6 months, we're on $12,050.55. A year after, year and a half after, 2 years after, so our 4th recursion. Okay, so after a further 2 years on, so in other words 6 years into the investment, the balance of the investment account will be $11,378.38. Alright, time to deal with calculating the interest associated with investments. Now it was easy with loan annuities or reducing loan balances because we only had to worry about paying off the loan. In investments, there are 2 lots of total interest we need to consider. The first is during the deposit phase, and you can work this out by looking at the difference between the balance you're after and the principal, and you minus off the number of compounding periods multiplied by the deposit amount you've been regularly putting into the account. When considering the interest earned during the withdrawal phase, however, similar formula, but you'll recognize that this withdrawal phase again is identical to working out the interest in a reducing loan balance account that's been charged. But in this case, you're earning the interest. Again, it's the difference between the balance and the principal, and instead of minusing in the withdrawal phase, we add on the number of compounding periods times the repayments that have been withdrawn. Okay, let's jump straight into an example. We have Damien, good old Damo. He invests $78,000 into an account. His investment is earning interest at the rate of 6.98% per annum, compounding monthly, with regular deposits of $500 per month. After 5 months, he plans to withdraw $700 per month for the next consecutive 6 months to pay off a bike he bought. So it steps us through what to do. So part A wants us to develop a recursion relation for the deposit phase. Part B, find the balance after 5 months. Part C, now develop a recursion relation for the withdrawal phase. Part D, find the balance after the next 6 months. And then lastly, part E, how much interest has he earned during this total 11-month period? So after processing that information, my deposit phase recurrence relation is going to be AN plus 1 equals 1.00582. Now it's a rounded rate times our current balance plus the $500 deposits every month. For part B, we want to know the balance of the account after 5 months. So we just set up our recursion relations in our calculator. So enter in our principal amount, 78,000, press equals, multiply it by the rate, then add on our monthly deposit amount. So after the first month, it'll be a balance of $78,953.96, which you should document, showing the reader of your response how you worked out that value. But from then on, it's okay if you just go through the iterations on your calculator. So we're after the 5th month, that's the 1st, 2nd, 3rd, 4th. The 5th month, he'll have a balance of $82,825.64. Alright, we then move on to the withdrawal phase. So this is where he's taking $700 per month for the next 6 consecutive months. Okay, so the first thing we need to do is redefine what's happening within our account. With the withdrawal phase recursion, all we're simply doing is we're changing the deposits of $500 to now withdrawals of $700, remembering that the account is still earning interest as time progresses. So remember, this also means that we redefine our principal amount since we're entering into a new phase. So that is our $82,825.64. And then we're simply applying our recursion formula. So enter in the new principal value, multiply it by the rate, subtract the regular withdrawal amounts. After the first month, we have $82,607.69, and we want to go all the way to that 6 months further. So 2nd, 3rd, 4th, 5th, 6th month, the balance will be $81,498.74. So that answers our part D. For part E, how much interest does Damien earn during this total 11-month period? So remember I said that means we have to work out how much interest he earned in the deposit phase, as well as working out how much interest he earned in that withdrawal phase. Okay, so just recalling the formula, deposit phase, I subtract the balance after 5 months from the initial principal of 78,000, and then minus the number of compounding periods by the deposit. Withdrawal phase, I just essentially do the same thing, except I'm adding on the number of times $700 was withdrawn. So if I pop those values in and then evaluate it, so for that first deposit phase, there was interest of $2,325.64. For the second withdrawal phase, there was $2,873.10 of interest earned, which altogether means that over that 11-month period, $5,198.74 of interest was earned. Alrighty, time to try some examples for yourself. So what I'd like you to do is press pause and have a decent go at these example questions 5, 6, and 7 yourself. Probably take you about 20 minutes to do, and then unpause the video and I will take you through the solutions. See you very shortly. Okay, how did you go? Let's go through question 5. So for A, hopefully your recurrence relation looks something like that. And if we're after the 7th month for part B, you would have found a balance of $8,743.64. For part C, after 2 years, that's the 24th recursion. So pumping that equals button on your calculator, hopefully you came up with a balance of $13,832.33. In terms of the interest earned during that 2 years, we take that final balance and we minus the principal, also taking off 24 lots of the $230 deposit, and interest earned over that 2 years of the investment would have been $1,512.33. Moving on to question 6. We got old Rich investing $120,000. I wish I had that much money into an account with no regular payments. So our regular deposits are $0. And we have an interest rate of 3.8% per annum, compounding monthly for 25 years. So because that first period doesn't have any regular repayments, this means we can go straight to using our compound interest formula to work out the balance of that account after the 25 years. Because there is no way I'm going to do 300 recursions on my calculator. After that 25 years, there should be a balance of $309,819.77. Now we can consider the second half of the question, which tells us he withdraws $2,400 a month as an income. So this means we're moving into a withdrawal period. Okay, so having a look at that, we must change our new starting balance or principal to be that 25-year balance. And considering our rate of 1.00317, that means my withdrawal recursion will look like this. And as I progress through the next 3 months, hopefully you had a balance on your account of $305,549.56 after he starts that withdrawing. Now if I work out the total interest during that whole 303-month time period, that means that the first part he would have earned $189,819.70 interest over that 25 years, as well as during the 3 months $2,929.23. So altogether he earned $192,749 interest. Question 7, we've got Peter investing $30,000 into an investment account compounding monthly, and the question's asking you to compare if he were to make deposits of $3,000 per month compared to $4,000 per month, and constructing a recurrence relation in order to calculate how much extra interest he would earn over the first 4 months of the investment. And it's definitely not a loan, so we'll cross that out. Okay, so if we compare those two deposit scenarios, looking through the $3,000 deposit scenario, we should have had a rate of 1.003042, and then if I set up my recursion, hopefully yours looks similar, and using my calculator, just pumping out those first 4 months of recursion. So after 4 months, he would have a balance of $42,421.53, which means that the interest he earned making those $3,000 deposits was $421.53 over the 4 months. Compare this to if he was making $4,000 deposit every month. You could see that the balance in the account after the 4 months was $46,439.82, which means that he would have earned $439.82 worth of interest. Now, interestingly, comparing the extra interest then earned, if I look at the difference between them, that's only a difference of $18.29 extra interest during that 4-month period, if he was paying $4,000 instead of $3,000. Okay, so hopefully this has helped you understand using recursion relations to model an investment annuity. And remember, there's 2 phases, the deposit phase and the withdrawal phase. And then secondly, when calculating the interest associated with investments, there's also two phases you need to consider when you're doing those interest calculations. Good luck with your practice questions. Thanks, Year 12s.